Imagine you are standing at the edge of everything you have ever known, looking out into the infinite darkness of space, dreaming of traveling to distant galaxies, of exploring alien worlds, of becoming a truly cosmic civilization. You close your eyes and picture yourself aboard a magnificent starship, cutting through the void at impossible speeds, visiting the Andromeda Galaxy as easily as taking a weekend trip to Paris. But then Richard Feynman's voice echoes in your mind, gentle yet devastating, explaining why this dream, this fundamental human desire to explore and escape our cosmic neighborhood, will forever remain just that, a dream. You open your eyes and realize that you are not just standing at the edge of your backyard, looking up at the stars. You are standing at the edge of an invisible prison, one whose walls are woven from the very fabric of space-time itself, whose locks are the fundamental constants of nature, whose keys were thrown away at the moment of the Big Bang. This prison is not made of steel or stone. It is made of something far more unbreakable, the speed of light. And Feynman, with his characteristic blend of wonder and devastating clarity, showed us exactly why these invisible chains can never be broken, why the universe has built-in barriers that make true cosmic freedom impossible, why we are forever trapped in our tiny corner of an incomprehensibly vast cosmos. Today, you're about to discover the most beautiful and terrifying truth that modern physics has ever revealed. The universe doesn't just have rules, it has walls. Invisible, impenetrable walls that separate us from almost everything that exists. Walls that ensure we will only ever see a tiny fraction of reality. Walls that Feynman understood better than perhaps anyone else. This isn't just about space travel or science fiction. This is about the fundamental architecture of existence itself, about why the universe is constructed in such a way that most of it must forever remain beyond our reach, no matter how clever we become, no matter how advanced our technology grows, no matter how desperately we dream of breaking free. Have you ever wondered why the universe seems to mock our ambitions? Why, every time we think we understand the rules well enough to transcend them, we discover new limitations, new barriers, new walls that confine us to our microscopic corner of existence. We build faster rockets, and the universe reminds us of the speed of light. We dream of unlimited energy, and thermodynamics laughs at us. We imagine perfect knowledge, and uncertainty principles smile knowingly. It's as if the cosmos was specifically designed to keep us humble, to keep us trapped, to ensure that no matter how far we think we've come, we're still just clever apes, barely able to see beyond our own solar system. But here's what most people don't realize. These aren't arbitrary limitations imposed by a cruel universe. These are fundamental features of reality itself, as inescapable as the fact that 2 + 2 = 4, as unavoidable as the existence of mathematical truth. The speed of light isn't just a speed limit for spaceships. It's the maximum rate at which cause and effect can propagate through space-time. It's the fundamental clock speed of reality itself. And this means something absolutely devastating for anyone who dreams of cosmic exploration. It means that the universe is not just big, it's unreachably big. Most of it will forever remain causally disconnected from us, hidden behind horizons that we can never cross, separated from us by distances that grow faster than light itself can travel. We like to think that the universe is our playground, that given enough time and technology, we could explore every galaxy, visit every star, unravel every mystery. But Feynman understood something that most people still haven't grasped. The universe isn't our playground. We're not even playing in the same league as the universe. We're not even in the same sport. Let's start with something that seems simple, but contains the seeds of our cosmic imprisonment. In 1676, a Danish astronomer named Ole Rømer was trying to solve a practical problem with the moons of Jupiter. He had been carefully timing the eclipses of Io, Jupiter's innermost large moon, expecting them to occur at perfectly regular intervals. But something strange was happening. When Earth was moving toward Jupiter in its orbit, The eclipses seemed to happen slightly earlier than predicted. When Earth was moving away from Jupiter, they seemed to happen slightly later. Other astronomers dismissed this as measurement error, but Rimmer had a revolutionary idea. What if light itself had a finite speed? What if those few extra minutes of delay weren't mistakes, but were actually telling us something profound about the nature of reality itself? He calculated that light must travel at approximately 140 horse-miles per second. The actual speed is 186, 282, 397 miles per second, but Rimmer's insight was revolutionary. Light wasn't instantaneous. Information itself had a speed limit, and this simple discovery would eventually reveal the invisible walls of our cosmic prison. Fast forward to the late 1800s, when James Clerk Maxwell was working out the mathematical relationships between electricity and magnetism. His equations predicted that electromagnetic waves, including light, must travel at a specific speed through empty space. Not approximately this speed, not usually this speed, but exactly this speed, determined by the fundamental electrical and magnetic properties of the vacuum itself. This wasn't just another measurement of how fast light happened to move. This was a revelation that the speed of light was woven into the basic structure of electromagnetic reality. And then came the Michelson-Morley experiment in 1887, one of the most famous null results in the history of science. Albert Michelson and Edward Morley set up an incredibly sensitive apparatus to measure Earth's motion through what physicists then called the luminiferous ether, the supposed medium through which light waves traveled. They expected to find that light traveled faster when moving with Earth's motion and slower when moving against it, just as sound travels faster with the wind and slower against it. But they found nothing. No matter which direction they pointed their apparatus, light traveled at exactly the same speed. This wasn't just puzzling. It was impossible, according to everything physicists thought they knew about motion and waves. A baseball thrown from a moving train travels faster relative to the ground than a baseball thrown from a stationary platform. Why didn't light behave the same way? The answer would shatter our understanding of space and time themselves. Now, I want you to pause for a moment and think about what you've just learned. We've discovered that light has a specific, unchanging speed, regardless of how fast its source is moving or how fast we're moving when we measure it. Before you continue, leave a comment below with your best guess about what this means for space travel. Do you think this speed limit can be overcome with enough technology? Do you think it's possible that some civilization somewhere in the universe has figured out how to break the light speed barrier? What's your intuition telling you? And more importantly, can you think of any everyday experience that might give us a clue about why the universe might have such a hard speed limit built into its very foundations? Share your thoughts in the comments, because the next part of this story is going to challenge everything you think you know about the possibility of escaping our cosmic neighborhood. And I want to know where your mind goes before we dive into the devastating reality that Feynman helped us understand. Albert Einstein was a young patent clerk in Bern when he realized that the Michelson-Morley result wasn't a mysterious anomaly. It was a window into the true nature of reality. In 1905, he published his special theory of relativity, which began with a simple but revolutionary postulate. The speed of light in a vacuum is the same for all observers, regardless of their motion. This sounds innocent enough until you follow it to its logical conclusions. If light always travels at the same speed relative to every observer, then space and time themselves must be flexible, must stretch and contract to accommodate this fundamental constant. When you travel faster, time slows down for you relative to stationary observers. When you travel faster, your length contracts in the direction of motion. These aren't just theoretical curiosities. They're measurable effects that we observe in particle accelerators every day. Effects that GPS satellites must account for to maintain accuracy, effects that make the universe far stranger than our everyday experience suggests. But Einstein didn't stop there. His general theory of relativity, published in 1915, revealed that massive objects warp the fabric of space-time itself. Gravity isn't a force pulling objects together. It's the curvature of space-time telling matter how to move. A planet orbits a star because the star's mass curves space-time in such a way that a straight line in four-dimensional space-time appears as an elliptical orbit in three-dimensional space. And this is where Richard Feynman enters our story with his characteristic brilliance and devastating clarity. Feynman understood that Einstein's theories weren't just describing how objects move through space and time. They were revealing the fundamental architecture of reality itself, an architecture that places absolute limits on what any intelligence, no matter how advanced, can ever achieve. In his lectures at Caltech, Feynman would often explain these concepts using thought experiments that made the impossible nature of faster-than-light travel crystal clear. Imagine, he would say, that you're trying to send a message to a friend on Alpha Centauri about 37 light-years away. Even if you could send that message at the speed of light, it would take 37 years to reach your friend and another 37 years for their reply to reach you. A simple conversation would take nearly 9 years, but what if you tried to send the message faster than light? Here's where Einstein's relativity reveals its most devastating implications. If faster-than-light travel were possible, it would allow you to travel backward in time, creating paradoxes that would undermine the very concept of cause and effect. Feynman demonstrated this with elegant mathematical precision. If you could travel to Alpha Centauri faster than light, turn around, and travel back to Earth faster than light, you could arrive before you left, potentially preventing your own departure and creating logical contradictions that would tear apart the fabric of rational reality. The mathematics behind this revelation are elegant and terrifying in their simplicity. Consider the Lorentz factor, a mathematical expression that appears throughout special relativity. It's written as gamma equals 1 divided by the square root of 1 minus v squared over c squared, where v is velocity and c is the speed of light. When your velocity is much smaller than the speed of light, this factor is approximately 1, and relativistic effects are negligible. But as your velocity approaches the speed of light, something dramatic happens. The denominator approaches 0, which means the Lorentz factor approaches infinity. What does this mean for a spaceship trying to reach light speed? It means that the energy required to accelerate the ship increases without bound as you approach the speed of light. To actually reach the speed of light would require infinite energy, which is impossible for any object with mass. But the story gets even more interesting when we consider what happens to time itself. The proper time experienced by travelers on a high-speed spacecraft is dilated relative to observers who remain stationary. If you could somehow travel at 9% of the speed of light to a star 1,000 light-years away, the journey would take about 1,000 years as measured by observers on Earth, but only about 45 years as experienced by the travelers. This might seem like a loophole that could allow practical interstellar travel, but it creates its own form of cosmic prison. The travelers become unstuck from the flow of time experienced by the rest of humanity. They could visit distant stars, but when they returned, everyone they ever knew would be long dead, and human civilization would have evolved beyond recognition. And even this scenario assumes we could somehow obtain the impossible energies required for near-light-speed travel. The kinetic energy of a spacecraft traveling at 99. 9% of the speed of light would be enormous, far beyond anything we could conceive of generating with any known physics. To accelerate even a small spacecraft to such speeds would require converting significant fractions of a planet's mass into pure energy. And we haven't even discussed the practical problems of interstellar dust and radiation at relativistic speeds, which would turn every tiny particle into a devastating cosmic ray that could destroy any conventional spacecraft. Feynman often pointed out that these limitations aren't technological problems waiting to be solved by clever engineering. They're fundamental features of the universe itself, as inescapable as the laws of mathematics, as permanent as the structure of space-time. The speed of light isn't just a speed limit for matter and energy. It's the maximum rate at which causality itself can propagate, the fundamental clock speed of reality, the ultimate cosmic speed limit that can never be exceeded without destroying the logical consistency of the universe itself. Now we come to the truly devastating implications of these discoveries, the invisible barriers that Feynman helped us understand with his uncompromising clarity about the nature of physical law. The observable universe is approximately 93 billion light-years in diameter, containing roughly 2 trillion galaxies, each with hundreds of billions of stars. But here's the cosmic joke that Feynman appreciated better than most. The vast majority of this universe will forever remain beyond our reach, not because of technological limitations, but because of the fundamental structure of space-time itself. The expansion of the universe, driven by dark energy, is accelerating. This means that galaxies beyond our local group are moving away from us at speeds that increase with distance. At a distance of about 16 billion light-years, galaxies are receding from us at the speed of light. Beyond this distance, which astronomers call the Hubble sphere, galaxies are receding faster than light, which is perfectly allowed by general relativity because it's space itself that's expanding, not objects moving through space. This creates what cosmologists call the particle horizon, a boundary beyond which we can never receive information, no matter how long we wait. But even more devastating is the event horizon, which represents the boundary beyond which we can never send information or travel, no matter how advanced our technology becomes. As dark energy continues to accelerate the expansion of the universe, this event horizon is actually shrinking. Galaxies that we can see today will eventually disappear beyond this boundary, becoming forever unreachable. In about 100 billion years, an observer in our galaxy will see a universe that appears to contain only the local group of galaxies. All evidence of the Big Bang, of cosmic evolution, of the larger structure of the universe, will have disappeared beyond the cosmological horizon. The universe will appear static and eternal, just as it did to astronomers before Edwin Hubble discovered cosmic expansion. This is the invisible barrier that Feynman understood we could never overcome. It's not made of matter or energy. It's made of the structure of spacetime itself, reinforced by the accelerating expansion driven by dark energy, protected by the fundamental speed limit of causality. No amount of technological advancement can change the basic geometry of an expanding universe. No amount of cleverness can overcome the fact that space itself is carrying distant galaxies away from us faster than any signal can travel between them. Even if we could somehow build spacecraft capable of traveling at substantial fractions of the speed of light, even if we could overcome the enormous energy requirements and engineering challenges, we would still be trapped in an ever-shrinking bubble of accessible space. The reachable universe is actually getting smaller with every passing moment, as more and more galaxies slip beyond our cosmic horizon, disappearing into regions of space-time that are causally disconnected from our own. Feynman often emphasized that physics isn't about what we want to be true or what seems reasonable, based on our everyday experience. Physics is about what the universe actually allows, regardless of our desires or intuitions. And what the universe allows is a cosmos, where most of reality must forever remain beyond our reach, where the fundamental laws of nature conspire to keep us isolated in our tiny corner of an incomprehensibly vast whole. The technological implications of these fundamental barriers extend into every aspect of interstellar travel and cosmic exploration. Consider the problem of propulsion for relativistic spacecraft. Chemical rockets, even the most advanced ones imaginable, can barely achieve exhaust velocities of a few kilometers per second. To reach even 10% of the speed of light would require specific impulses hundreds of thousands of times greater than any chemical reaction can provide. Nuclear fusion, often touted as the solution to our energy needs, could theoretically provide specific impulses about 100 times better than chemical rockets. But this would still fall woefully short of relativistic requirements. Even antimatter annihilation, which converts mass to energy with 100% efficiency, would face enormous practical challenges. A spacecraft using antimatter propulsion would need to carry vast quantities of antimatter fuel, but antimatter is the most expensive substance ever created, costing trillions of dollars per gram using current production methods. Moreover, storing antimatter requires magnetic containment systems that would themselves have enormous mass, reducing the effective specific impulse of the propulsion system. The tyranny of the rocket equation ensures that any spacecraft must carry exponentially more fuel for exponentially higher final velocities. To accelerate a payload to relativistic speeds using conventional propulsion would require fuel masses many times greater than the mass of entire planets. But let's imagine, for the sake of argument, that some advanced civilization could somehow overcome these propulsion challenges. Perhaps they discover new physics that allows them to manipulate space-time directly. Or they build massive laser arrays to push light sails to relativistic speeds. Even then, they would face the problem of interstellar navigation at speeds where time dilation becomes significant. At 90% of the speed of light, time dilation becomes severe enough that a journey to a star 100 light-years away would take about 111 years as measured from the home planet, but only about 44 years as experienced by the travelers. Communication with home base would become increasingly difficult as radio signals would be severely Doppler shifted and time delayed. More fundamentally, the travelers would become unstuck from their civilization's timeline, returning to find that more than 2 centuries had passed and everyone they knew was long dead. This temporal isolation represents another form of cosmic barrier, one that makes true interstellar civilization extremely difficult, even if the propulsion problems could somehow be solved. Each voyage becomes a one-way journey, not just through space, but through time itself, severing the connections that bind travelers to their origins. Modern proposals for interstellar travel often invoke concepts like generation ships, spacecraft large enough to support entire populations for the centuries or millennia required for interstellar journeys at sub-relativistic speeds. But the engineering challenges of such vessels are staggering. They would need to be essentially self-contained worlds, capable of maintaining complex ecosystems for hundreds of generations, with redundant life support systems, manufacturing capabilities, and social structures stable enough to survive the isolation of interstellar space. The psychological and sociological challenges might be even more daunting than the engineering ones. How do you maintain motivation and social cohesion across generations of people who will never see their destination? How do you preserve knowledge and culture across centuries of isolation? How do you prevent the kind of technological regression that might leave a generation ship stranded between the stars with no way to complete its mission? Even if we could somehow solve all of these problems, even if we could build relativistic spacecraft and generation ships and maintain interstellar civilizations across vast distances and time scales, we would still be confined to our immediate cosmic neighborhood. The local group of galaxies, consisting of the Milky Way, Andromeda, and about 80 smaller galaxies, represents the largest structure that will ever be accessible to us. Beyond the local group, the expansion of space ensures that all other galaxies are receding from us at speeds that make them forever unreachable. This represents a volume of space containing perhaps 1 trillion stars, which sounds vast, until you realize it's less than 1/10,000th of 1% of the observable universe. We are like bacteria in a petri dish, able to explore our small container, but forever unable to reach the vast laboratory beyond. The cosmic microwave background radiation, the afterglow of the Big Bang that pervades all of space, provides a constant reminder of this limitation. As we look deeper into space, we look further back in time until we reach the surface of last scattering about 380 solar years after the Big Bang. Beyond this distance, the universe was opaque to electromagnetic radiation, creating an absolute horizon beyond which we can never see using conventional astronomy. This represents both a spatial and temporal boundary, a wall that separates us from the earliest moments of cosmic history. Feynman often emphasized that these limitations aren't temporary inconveniences waiting to be overcome by future technological developments. They're permanent features of the universe itself, encoded in the fundamental constants of nature, enforced by the basic structure of space-time. The speed of light, Planck's constant, the cosmological constant that drives dark energy, these aren't arbitrary numbers chosen by some cosmic legislator. They're intrinsic properties of reality that determine what kinds of universes are possible and what kinds of physics can exist within them. In our universe, the physics allows for the existence of complex structures like stars and planets and life. But it also ensures that most of the universe must forever remain beyond the reach of any intelligence, no matter how advanced. This might seem like a cruel cosmic joke, but Feynman understood that it's also what makes our universe interesting and stable. If the speed of light were infinite, causality would break down and coherent physical law would be impossible. If dark energy didn't exist, the universe might collapse back on itself before life could evolve. The very barriers that confine us to our cosmic neighborhood are also what make our cosmic neighborhood habitable. We live in a universe that's vast enough to be interesting, but constrained enough to be stable, large enough to contain countless wonders, but small enough in its accessible portion to prevent the kind of causal chaos that would make complex structures impossible. If you're starting to understand the profound implications of what we've been discussing, if you're beginning to grasp why Feynman considered these physical limitations to be among the most beautiful and terrible truths that science has ever revealed, then I want you to take a moment to show your appreciation by clicking the like button below. This kind of deep dive into fundamental physics takes enormous time and research to get right, and your support helps me continue creating content that explores the most mind-bending aspects of our universe. And if you haven't subscribed yet, please consider doing so and ringing the bell for notifications, because we're just scratching the surface of the cosmic mysteries that modern physics has revealed to us. So here we are, at the end of our journey through the invisible barriers of the universe, standing once again at the edge of everything we have ever known, but now with the devastating clarity that Feynman brought to our understanding of cosmic reality. We began by dreaming of traveling to distant galaxies, of escaping our cosmic neighborhood, of becoming a truly space-faring civilization with unlimited reach across the cosmos. But we discovered that the universe has other plans for us. The speed of light isn't just a speed limit for spacecraft. It's the fundamental clock speed of reality itself, the maximum rate at which cause and effect can propagate through space-time, the ultimate barrier that can never be crossed without destroying the logical consistency of the universe. The expansion of space driven by dark energy is carrying distant galaxies away from us faster than any signal can travel between them, creating event horizons beyond which we can never communicate or travel, no matter how advanced our technology becomes. Even the galaxies we can see today are slowly disappearing behind these cosmic horizons, leaving us increasingly isolated in an ever-shrinking bubble of accessible space. This isn't a temporary problem waiting to be solved by clever engineering. This is the fundamental architecture of reality, as permanent and inescapable as the laws of mathematics themselves. Feynman understood that physics isn't about what we want to be true. It's about what the universe actually allows. And what the universe allows is a cosmos where most of reality must forever remain beyond our reach, where the very laws that make life and intelligence possible also ensure that we can never escape our cosmic neighborhood. But perhaps this is as it should be. Perhaps the barriers that confine us are also what protect us, what make our corner of the universe stable and predictable and safe for the evolution of complex structures like life and consciousness. Perhaps the invisible walls of our cosmic prison are also the foundations of our cosmic home. We may never travel to distant galaxies or explore the far reaches of the universe, but we can understand these places through the power of scientific reasoning and mathematical insight. We can decode the messages that light brings us from cosmic horizons, can decipher the fundamental laws that govern all of reality, can appreciate the elegant mathematical structures that underlie the apparent chaos of natural phenomena. In the end, Feynman taught us that the universe's refusal to let us escape our cosmic neighborhood isn't a cruel limitation imposed by an indifferent cosmos. It's a profound truth about the nature of reality itself, a reminder that we live in a universe governed by beautiful, inexorable, and ultimately unbreakable physical laws. And in understanding these laws, in appreciating their elegance and their implications, we achieve a kind of freedom that transcends the mere ability to travel between the stars. We achieve the freedom of true knowledge.